I sent to you is for this process control is the briefing will be on the let me just delete these things. Okay, the briefing will be on the we're gonna split the laboratory will be coming starting on the Friday on the Friday 1st April. Okay, so you basically goes into two different groups. Okay, so in the first group, all 5 of you will be coming into the lab to be shown how to use that the equipment in the lab. That's basically a multi-processes bench that contains the flow control, okay, the temperature control, the pressure control, and the liquid level control. Okay, you guys have gotten an announcement that the open-ended sessions is going to be broken into two and divided into two. Basically, this one is the date and the time for the first open-ended session, and the due will be here. Okay, this is the first group number has been, and then the second open-ended sessions will be using the CEE30007 tutorial sessions. I have talked with Miss Lai, basically. Okay, so you all get the announcement like in here already, right? The briefing session will be on the 1st April. So for the first 3 groups in here, which include Alvin, Daniel, Jonathan, Sakya, Yusi, Amanda, Tiffany, Selena, Juliana, Chising, Clarence, and Jason will be on the will fit in here. Okay, so you will go into the open-ended session, the first one on the Friday, 8 April. The second open-ended sessions will be Taha, Usman, James, Michael, Wong Yo, Safaf, Rachel, Esandi, and Weising. Okay, that will be this fit within these things. Okay, I just want to reiterate these things again, so you guys just be prepared to track your your timetable. Just put it into your timetable. So the Friday 1st April will be your Friday 1st April will be, what is it? That will be week 5 if not wrong. Okay, so then you will have in the week 6 you will have the open-ended sessions with your, we will have a test as well in here. Okay, then your Aspen Plus will run on the week starting on the tuition week. Okay, so we will try to finish earlier, I think on the week 12. For the material so far, is there any questions? If there is no questions, then we will go into the week 4 materials for the process control and measurements. Okay, before we go into the feedback control, we will first discuss the dynamic behavior of the first order systems. Okay, so this week we try to cover these things, dynamic behavior of first order systems, and in the next lecture I'll try to cover some of the week 5 materials as well, and then I will open up sessions for you to ask about your project 1. This Friday, Frederick will give you an online sessions on the project 1. Okay, but if you want to ask either me or Frederick, then it's also fine. The Thursday sessions will be online because our postgrad have exposed to the positive cases in the postgraduate office. So for your safety, we choose to swap these tutorial sessions to be online. And then if everything going well, then next week we will switch again to the hybrid delivery for the tutorial again. It will be announced. Okay. So what do we cover for today? Is here. Okay. We want at the end of this lecture, you should be able to determine the dynamic behavior of chemical processes that are classified as first order process. And then we will also discuss the characteristic parameters of a first order process. We will also overview the various test input that is used for the dynamic analysis of the systems. And then we will also derive the expression for the transient response of different inputs. So first order system is a process whose output is modeled by a first order differential equation. Imagine you have a process, you have an input, and the input in here is a function is in terms of the change with time. It varies with time. That's why we label it as f bracket inside is t. The output here is y and then t, because we have discussed in the last week about the single input, single output as well. Okay, now let the dynamic model of this process represented by a first order ODE given below in the deviation variable form. Okay, because why do we use a deviation variable? Because if we use a deviation variable, it will make our life easy, because at the time equals 0, basically the deviations will be 0, because we assume that at time t equals 0, then the value of the variable of the interest will be at steady state. Okay, so in here you see in the equation 1, we can break down into two cases where a naught is equal to 0 and the a naught is not equal to 0. So let's say if the first one, a naught is not equal 0, what we will do in here? What we do is we can rearrange. Okay, when we rearrange, then this constant in here can be taken as equal to the time constant of the process, whereas this one will be equal to the steady state gain. Okay, so that's just a thing that you want to check the unit again in here. So if we do it like this, if we take this constant as in a time constant of the process, this one as a steady state gain, then the final equation form will becomes this equation 2. Okay, how do we want to solve these things in here? So the way that we gonna go with this system is we can solve it by using a Laplace transform, because in here we are dealing with the linear ordinary differential equations. So what we can do is we assume that the system is originally at the steady state to eliminate f naught and y naught in here. Okay, what we do in here is we follow these things in here. Okay, so basically we Laplace transform this left hand side, we Laplace transform the right hand side. If we do so, we will be able to get this, and then we will be able to get the transfer function. The transfer function in here is called a first order lag, or simply first order transfer function. Okay, so you can see in here in this form that you have the so-called time constant in here, and you have a steady state gain on the numerator. In the denominator, on the other hand, you have the time constant of the process. For the second case, when a naught is equal 0, that will be simple, because once you put this thing equal 0, then you will only have this term and this term in here. Okay, that means you only these things in here is can be represented physically in terms of the steady state gain. Then you can solve it again in the similar way. You can use a Laplace transform, and you will get another transfer function. So the transfer function that you have for the case of a naught not equal to 0 is different with the transfer function when a naught is equal to 0. This one is Kp divided by S. This type of process is called purely capacitive or pure integrator. Okay. Now we go into the example. So if we have these things in here, we want to understand what are the we want to infer what is the process gain and the time constant of the process. So you want to make this in terms of this form in here. So you need to divide the numerator by the numerator or the denominator by 4 and by 4. So this here you have this equal to this term in here. So you know that your Kp is equal minus 0.5 and your time constant is equal 5.5. Okay, so this one is just an easy example. If we have this kind of transfer functions, if we want to know what are the steady state gain, and then what are the time constant for that particular first order process, then we need to equalize this form with respect to this form to get the value of the steady state gain and the value of the time constant. Now, more importantly is in chemical engineering process, if we so process control is not something that has been it's not something that is new. So process control has been developed since 1980, so it's about 30 or 40 years. So everything that people knows about the process control has been established. Okay, so the reason that we go into this first order process is because we want to look back into what chemical engineering processes that are belong to the first order process, so that we know how to relate all the models that we develop in here, and then what is the characteristic nature of that. With is it a self-controlling process, or do we need an additional of the control systems to regulate the first order systems? So for the first order system, there are two important characteristics. The first important characteristic is the capacity to store material, energy, or momentum. And then we also have the resistance associated with the flow of mass, energy, or momentum in reaching the capacity. So the examples in here are the dynamic response of the tanks. So if that is a liquid storage tank, okay, that will have the capacity to store liquids or also gases. The resistance, on the other hand, is associated with the pump, valve, weirs, pipes that are attached to the inflow or the outflow of the liquids or gases. So at this particular point, it may not be clear to you yet what I meant. So that's why we have to go into the example to explain this, the significance of this. Okay. So in this particular example, for example, we are dealing with the mass storage tank with the capacity for mass storage. So you see this kind of systems. In here, we can define that the outlet flow is equal to the height of the liquid divided by the R. If we take a mass balance in terms of the accumulations is equal in minus out, then we will know that this equation applies. Okay, then we substitute this with this H divided by R. Now, if we keep on doing that thing, then we multiply the left and right hand sides by the R. Okay, in order to make it into a particular form that can fit into our equations in here, right? So we continue this, and then we move this H into the left hand side, and we took that the value at the steady state in here will be equal to this. Okay, so when we take the value at the steady state, is that we substitute this value, this H with the HS, this H with the HS, and then this value in here with the value at the steady state. Okay, so if we subtract this from this, then we will be able to get the particular value in terms of the deviation variables in here. Okay, but you need to really being particular in this kind of things. You need to know which one is the dependent variables. Your dependent variables in this respect is the H and Fi in here. Okay, that's why you need to swap them with their value at the steady state in here. Once you get into the deviation variables, then you can define this AR is equal to the time constant of the process, and the Kp is equal to the R. So this one is with regard to these derivations that we deal with the problem that A naught is not equal to 0. So basically you convert this AI divided by AO, which in this case is basically AR, and this B divided by A naught into the steady state gain. Okay, so it's just going back into inspections of your mathematical form. If you take a Laplace transform, you will be able to get this typical form again, the same form in here. right? With the special note that your Kp in here is equal to the R, and your time constant, which is the tau p in here, is equal to the AR. Then the things that you can do by inspecting into your equations is that the cross-sectional area in here is a measure of the capacity to store the mass. Why? Because the larger the cross-sections of your tank, the more liquid you can store within your tank. Okay, this is why. And then since your time constant of the process is A multiplied by R, we can say that the time constant here have a relationship that in terms of the storage capacity multiplied by the resistance to flow. Okay, so this things is basically is very important, more important than deriving all these things is the you take some time, you reflect back the mathematical model, you check back how did you connect those mathematical model in terms of the physical significance. So it's very important that you look back into the physics of the system. That's why when we go into chemical engineering, we are dealing a lot with the mathematical and the physical concept. Okay, we only using a superficial concept of chemistry in chemical engineering actually. Okay, now I try to press it again. Then we go into the other example now. Now in here, the first one, the example that we have just discussed is talking about the liquid storage. Now we are talking about the energy storage. Okay, so let's imagine that we have this kind of tank. The liquid in the tank is heated by saturated steam, which flow through a coil immersed in the liquid. So there is a heat transfer between the coil with the liquid. Okay, and then this tank is also a stir tank as well. So what do we do with this one? Okay, we do the energy balance in here. Okay, we do the energy balance because there is only an accumulation is equal to the input. Okay, we take the boundary over this liquid in here, so we don't have the in the assumptions for the systems that we draw in here, where you need to pay attention carefully in here that we only have an input, we don't have the output. The output will be different if that is for a different system. So this is where we have these particular equations, and then we can take assumptions that the rho, volume, and the Cp is constant because there is no inlet or no outlet into the tank, right? And then the heat provided by the coil in here can be given in terms of these things in here, and then the TST in here define the temperature of the steam. Okay, in here is basically overall heat transfer coefficient, and then the area of the heat transfer is AT in here. Okay, so if we derive these things in here, we can get these equations in here. Now we take the value of the steady state. The value of the steady state is we change this value of the T into the steady state. This TS, this T become TS, TST become TST at steady state, T become T at steady state. Okay, this subtracted by this, we will get this deviation variables in here. Okay, then we move these two terms in here into the denominator of this term in here. Okay, and then we move this into the left hand side. Then we define the two variables. These things in here will be equal to the time constant of the process, and then we can also find out that your Kp will be equal to 1. Next, what we did is we take a Laplace transform. Then we know that our we can also infer again the case where our time constant will be equal to this density multiplied by the volume multiplied by the heat capacity at constant pressure divided by the overall heat transfer coefficients multiplied by the area of the heat transfer, whereas the Kp will be equal to 1. So the same with the previous example. The tank system has the capacity to store thermal energy and exhibit resistance to heat flow. That is expressed in terms of the U. Okay, the capacity for thermal energy storage is represented by this value, rho V Cp. The resistance to the flow of the heat from steam to liquid is represented by the value of 1 divided by U AP. Therefore, we see again that the same type of relationship holds where the time constant is equal to the storage capacity multiplied by the resistance to heat flow. So in the first one, it was what about liquid storage. In the second one, it's about the energy storage. Okay. Hi, good afternoon, Selena. The previous cases that we dealt with is dealing with the case where A naught is not equal to 0. Now, the next example, we'll talk about the pure capacitive system. Instead of putting in the thing that we discussed earlier, we derive the example 2 with one difference. The effluent flow rate is determined by the constant displacement pump, meaning that the flow rate in here is constant because we can adjust the flow rate using a pump. So no matter what the conditions is, we can define the flow rate of the pump to be constant. The flow rate that is taken out of this tank to be constant because it's determined by the pump. Okay. So if we take these things, then the mass balance will give us this. Okay. And you can see that at the steady state, this H will be an HS, Fi will be Fis, but Fo will be constant because we use a pump in here. Okay, meaning there should be no variations in terms of the flow rate. Therefore, if you use a deviation variable, this will be minus with this will be equal to 0. Minus of this plus this will be equal to 0. So you have these things in here, which you can define as a Kp. Kp is equal 1 over A. Then you can get this dH over dt is equal Kp Fi. Once you take the Laplace transform, you will get this. Then your Gs or the transfer functions will be equal to the Kp divided by S. So in essence, you are recovering the form where your A naught is equal to 0. So if you go back here again, you will get this transfer function Kp divided by S. So this one is called the purely capacitive or pure integrator. Okay. So the Kp in here is equal 1 over A. Now, unlike the case where the A naught is equal to not equal to 0, the pure capacitive process in here although it has the capacity to store mass, energy, or momentum, it has no resistance associated with the flow of mass, energy, or momentum in reaching the capacity. Okay, so the lack of such resistance is generally not encountered in real physical phenomena, in natural phenomena. Okay, so if you replace this pump with just a hole, okay, so it will go down by gravity, then you will not have something like this. Okay, but rather what you will have is something like this. Okay, because even if you use a gravity, then the flow rate of what comes out in here should be correlated with the height of the liquid and also with the gravity as well. So we will have consequences with the pure capacity process in terms of the control that we will discuss in the following slides. Okay. Now we know that for a first order transfer function, we know that this is the output, this is the input, and this one is the transfer function that are represented in terms of the Laplace domain. Okay, so the general time domain solution can be found once the nature of the input change is specified. The solution applies to any other process with a first order transfer function. What we want to do in here is overviewing several functions that you can use as your input for checking the dynamic behavior of your system. The first one in here is the step input. So if we have a sudden change in terms of the variables, it's called initially is 0, and then at time t equals 0, that value is increased to a. Okay, then your input will have a form like this in the Laplace form. Okay, we have a special case that if a equal 1, that means we have a unit step change. The next one will be the ramp input. The ramp input is something that have a change like this, so that it's increasing linearly with time in here. Okay, so the sample of the step input is something that exists in the reality. So if, for example, if suddenly a reactor feedstock is suddenly switched from one supply to the another, that may cause a change in the feed concentration. Okay, also that can be happening in terms of the flow as well, and any other things such as temperature as well, that is possible. Okay, the ramp input on the other hand is meaning that you increase that the value proportionally with time. Okay, in here we don't really have a limit in here, but of course in reality this will not be impossible. This will not be possible. So you may not you may have a limit in here. Okay, so in reality, what you will have for the ramp input is that something like a heat exchanger falling, loss in catalytic activity, or the exposure to ambient temperature. Okay, we also have something that we call the rectangular pulse. So at time t equals 0, any particular variable, for example, it can be a temperature, it can be a concentration, it can be a flow rate. It's going up to a particular value and then stay in that particular value for some time. It's called TW. Then it goes back to 0 again. A function like this is called the rectangular pulse input function. So if we put it, we represent it in terms of the time domain, it will be this. And if we use a Laplace transform, then it will be reflected by this particular formula. So the example of rectangular pulse input is if the reactor feed is shut off for 1 hour, or the fuel gas supply to a furnace is briefly interrupted. Okay. Next one that we will have is a sinusoidal input, which is in this case is a periodic or cyclic disturbances. So in terms of the time domain, you will have something like this that start at 0. Okay. This is if you use a sinus, right? If you use a cosinus, then you will start with the value in here. Okay, that goes down in here. Okay. If you use a Laplace transform, then you will have these things in here. Okay. Example of a sinusoidal input in here is the 24-hour variations in cooling water temperature. Then we have another functions that are quite interesting in here. It's called the impulse input or the direct delta function. So the impulse function in here is defined as equal to 0 at all time, except at t equals 0. But this is something like you basically put it a shot in here, okay, such that the area of whatever the shot in there is basically equal to 1. Okay, so if you use a Laplace transform, then it will be equal to 1. This function is used to represent a short transient disturbance, such as the injection of a tracer die. So what is important in this process inputs are all of them have is being used to represent the disturbances to a dynamic system. So for example, for the step input in here, these mathematical functions can be used to simulate a change in terms of the reactor feedstock. Okay, in here it can be used to simulate the heat exchanger falling or loss in catalyst activity. In here, it can be used to simulate a disturbance in terms of the interruptions of the fuel gas supply for a brief period of time. And then in here is if there is a variations in the cooling water temperature. In here, if you have a particular special case like injections of a tracer dye. Now you will ask me, sir, why you are why you need to bother with that different test inputs? Because now what you need to get is the dynamic response. If you have a first order transfer function, which is coupled with a particular input. Okay, so let's have a look if you have this particular first order transfer function, and then we assume that we have a step change in the input of magnitude A. So your FT will have these things. So in the Laplace domain it will be this, and you can get the output of your the dynamic output of your first order process by multiplying with your step input in here. Okay, so if you multiply this, that will be A divided by S. So you will have these things in here. These things in here, if you go into the Laplace transform on your week 2, you can inverse back again your transform in here. That will be equal to these things in here, Ka equal to 1 minus A minus raised to minus T divided by the time constant. Then you want to plot your systems. So in case you have this kind of a step input, how does your output behave? So your output will behave in such a way where it is basically having a magnitude of Ka. So if you divide this Yt divided by Ka, you will have something like this. So there will be a large change in the beginning, but after your T divided by the time constant is above 3, then the change will be quite marginal in here. Okay, so what is the main conclusions that you get in here? When you have a first order process with your A naught is not equal to 0, then that first order process is basically self-regulating. Self-regulating means that if you put in a disturbance into that system, the output of the systems will not become infinite, because infinite will be something that is dangerous. Imagine if you change the temperature by a step, you move it into a new value. If we don't get a new steady state value, then we will have an issue with that thing, meaning we have to install the control systems into that systems to make it stable. Okay, these things is quite important. You can check again. What can we infer again from this particular system is that the shape of the curve is monotonic with the maximum rate of change occurs when the inlet step change takes place. Okay, the manner in which the variable changes from its initial to final value is influenced by the time constant. That's why we put in this T divided by the tau, or this one is what we call dimensional time. Okay, this is what we call the dimensional output. Then we go into another example. Example 6 is the dynamic model of a certain process in deviation variable form. Okay, we have this one is an output variable. M in here is defined as the manipulated variable. D is disturbance. T is time. We are asked to determine the transfer function of the process, determine the time constants and steady state gain of the process, analyze the response of the process if the manipulated variable increases by 2.5 and is maintained there, determine the time the process takes to reach 99.3% of the new steady state value. Okay, we go with the first one first. We apply a Laplace transform into the left-hand side and the right-hand side. Okay. Then we rearrange, because we have a manipulated and we have a disturbance variables in here, meaning we have a two different transfer function. We want to make it in the form of the first order transfer function. So we divide the numerator and the denominator by 2. then we get this. Okay. Therefore, your transfer functions with respect to the manipulated variable will be this. The transfer functions with respect to the disturbance variable will be this. The time constant are the same for both correlations with the manipulated and disturbance. It will be 3.6. But the steady state gain with respect to the manipulated and with respect to the disturbance variable will be different. Okay. Next, we want to analyze the response of the process if the manipulated variable increases by 2.5. So that will be a step input by 2.5 times. Okay. So if you check these things, you apply Laplace transform, you will get this one. So the problem specify if the manipulated variable increases by 2.5. Okay. So you will get these things. Then you put in the Laplace transform. You will get this one again. This one coming from the table 2 in your week 2 lecture. The last questions dealing with determine the time the process takes to reach 99.3% of the new steady state value. So you put in 0.993. This equal to this. Okay, you do you apply logarithmic nature to change this form into this form in here. Then we know that we need about 18 minutes for the process to achieve 99.3% of the new steady state value. Okay, so concluding everything that we discussed so far, that the two constants that characterizes a first order systems are the time constant of the process, which is this tau p, and the steady state gain kp. The time constant, or tau p, is a measure of how long a process takes to adjust itself to the new value of an input. Okay. Whereas the kp indicates the size of the change in the steady state value of an output due to a unit input. So we are dealing with this case for a first order process where A0 is not equal to 0. We have a second case where the A0 is equal to 0. There will be a purely capacitive process that arises from a process that has only capacity and no resistance to the flow of mass or energy in reaching the process. This is a self-regulating process. This is a non-self-regulating process. So if we have this kind of things, then we may need to apply a control systems to make sure that the purely capacitive process will not create a problem for us when it operates. Okay. So any questions up to this particular points? Everybody? Rachel, Alvin, Amanda, Sandy, Clarence, Daniel, James, Jason, Jonathan, Cising, Michael, Taha, Usman, Rachel, Selena, Tiffany, Yusi, Wongyo, Weising. Everything is quite straightforward in here, and this one is a basic concept that are important in process control. So you need to familiarize yourself with this. Why not at the steady state? Which one is that why not in here? Because all of this is defined in terms of the deviation variables, you see. Okay, so this is why in here, without putting the dash in here, is in the steady state. So the deviation variables will be equal to 0 at time t equals 0 because there will be no deviations from the steady state. Okay, so the deviation with respect to the steady state is equal to 0. So that's why we all this is all defined in terms of the deviation variable. So if you check, this one is the deviation variable. If you check which one is that, everything in here is basically a deviation variables that we go and find from the beginning. Everything is the deviation, just for the sake of making your life simple by getting all these things become zero at the steady state. Okay, this one is at steady state. This things is something where we call a regulatory problem, where the disturbance is with respect to the steady state condition. If we are dealing with something with the servo problem, then it's different. Servo problem is we basically control the trajectory of the systems with time. Okay, you get what I meant, you see? Or we can set up another time for us to speak in detail. If we meet in face-to-face, then you can ask me why this is the case, because this variable in here is implying the, yeah, this, if you put it like in y dash, yeah, it is y dash, but because we already say that this is represented in terms of the deviation variable, then not all variables we need to define in terms of this y action, right? So when we mention something about the deviations, then it's already clear to us that not every symbols that in here we have to put it in terms of the y action. Yes, correct. That's correct. That's correct. It's just a problem of notations, I think. So sometimes it may be confusing a little bit in terms of the notations. But everything in here is defined pretty much in terms of the deviation variable, and unless if it is defined otherwise. Okay. So what else again that I want to show you? So the MATLAB files for your project one. So Friday Frederick will go and talk again. For the, I think most of you also doing the process modeling as well, right? So what you need to do is, I know that the MATLAB online has been working. So for your process modeling, make sure that you put everything into the same folder. Okay, for example, this one is the project 45. I have this project 45. I have a lot of folders where I put in here different project for checking your process modeling. So let's say I open this one. You need to put in all the files into the same MATLAB files into the same folder. Let me try opening this one, for example. Okay. The problem associated with this access problem is because we are renewing the license. Okay, so we get it done. So we open this one, the get FM. Okay, and then we open this IVP RK for control. Okay, and then we open this LLDC driver.m. Okay, so what happens in here is you open these three things at the same time, right? In order for you to run these things, then you just click in here, you run. Okay, it may take some time because MATLAB Online is probably a bit slow. So this is the figure one. Figure one is basically comparing the linear model with the nonlinear model. If you have a decrease of 10% in Q, this one is 85% in Q in terms of the flow rate. Okay. Then this figure 2 is basically giving you the response if you run the with the proportional controller. So what essentially why you need to open these three code at the same time? This one is the one that you run because this LLDC driver is the one that will call these things in here. Okay. So this will call this function in here to calculate the value of A and B. And then after that, it will also calculate the value of G and H as well. Okay, depending on what you are putting into this into these things in here. This IVP RK for control will call this getF in here. Okay, so that's why you need a different functions, because everything is interrelated with each other. And then this LLDC driver will be the one that plots the results in here. Okay, whatever the matrix you have in here, it will be plotted by these things in here. Okay, I think you can also access the MATLAB online for your process control as well at the same time that I have shown to you before. So guys, is there any questions? If not, then I think the next lecture that we have for this week, I will go into covering the week 5 materials to make it a bit more a bit more fast. And then after that, then we will let you relax a little bit when you have much more tests or assignments that came in, and we can have a meeting. So the lecture will probably be replaced with individual group sessions. If you need to have meeting with me to discuss your project, either project 1 for process control or your project 1 with your process modeling. If there is no more questions, then I'll stop my recording in here. Okay.